Hey, this week we're going to be visualizing time and relative dimensions in space. Specifically, in this first video, we're going to be going through how to visualize temporal data. Now, I'm sure you've all seen some visualizations of temporal data, as in data that changes over time before, but I just wanted to spend a video focusing on it because I think it's a really core part of how to be a good data visualization designer. Take a look at this example from Randall Munroe's excellent XKCD comic. So take a look at this example from Randall Munroe's excellent XKCD. It's showing the global average temperature over time from about 20,000 years ago. You can see that average line moving slowly. Know that each of these ticks is about 500 years, and he's lined it up with various different events in the history of civilization. Actually, civilization just started now. Now we can see the last 2,000 years. Then, whoa, what's that happening right down the bottom there? A visualization like this gives you an idea of the temporal component at which things change. Some people will say, but the global average temperature has been changing all along. Well, I think if you look at this, you'll see that maybe the changes that have happened in the last 200 years are happening on a slightly different time scale. And it's that kind of thing, showing temporal changes and the rate at which changes accelerate, that visualization of temporal data is excellent for showing. I encourage you to go to the link and check out this visualization in detail. There's a lot of really fun things in there on the way the world has changed over time and the history of civilization. Maybe you're not a nerd and you're not as into that stuff as I am, but maybe you are. So from the very beginning, we've been talking about visualizations that have a temporal component that show data changing over time. The very most basic chart that most of us learn, the line graph, is usually plotted with time on the x-axis, right? It isn't actually in this example, but this is that DataViz project slide we talked about earlier. Usually you're talking about something changing over time, whether it's carbon emissions, a stock price, coronavirus cases. In each case, it's a quantity, that single quantity per line that is changing over time. But this is just one of many ways of showing temporal data and how it changes. You can actually go all the way back to one of the first visualizations. In fact, this, remember we talked about in the history lecture, this is probably one of the first real visualizations of statistical data by William Playfair in the late 1700s. And this is an area chart showing two series and then highlighting the difference in between them, because this is the amount of imports and the amount of exports between England and various European countries. And you can see here that when imports are greater than exports, there's a balance of trade against. And then when exports are greater than imports, there's a balance of trade in favor. We now call these trade surplus and trade deficit, and they're a little bit more complicated than they were in the late 1700s. But you can see here the point that Playfair is trying to make is that England is exporting a lot more goods and therefore making money from the rest of Europe. So this visualization, way back from the beginning, is looking at changes over time and what those changes have added up to in terms of England's economy. But there are other ways of looking at this. This is one of my absolute favorite visualizations of everything that's wrong with Twitter. The left, I guess, clock, you could call it. This is called a spiral chart sometimes. This shows the points, little bumps, the points in time at which this Twitter account posts from midnight at the top all the way around over a 24-hour period. And you can see that the vast majority of the time, this person posts between noon and 10 p.m., because that's the time period where we're all trolling social media. And that one time they posted at 3 in the morning, that was I'm going to assume a drunk tweet. But usually it's a fairly uneven pattern. Compare with the one on the right, which is a Twitter account suspected of being a bot. Do you notice that this bot posts exactly every 6 hours? This kind of pattern of activity is not something you would expect a human to do, but looking at it this way, rather than just seeing the timestamps of the activity, you can really see the difference. These are some of the things that go into detecting bot activity on Twitter. It's not that you couldn't write a bot that would post with a more natural signature. It's just that people usually don't bother. Here's another example of that same phenomenon. This is by the Knight Foundation, who've done a great deal of work investigating mis- and disinformation in social media, particularly tied to the US elections, but I think they're looking at the problem more broadly. That's just the place where it's a kind of big deal. This is a hashtag, the No Dakota Access Pipeline hashtag, which was originally a progressive cause. So you can see the red dots before the 27th here on the visualization are those classified as accounts with a liberal or progressive bias inside the US. You can see originally this is people campaigning against the establishment of a large new oil pipeline. And then all of a sudden, in one would argue perhaps an unnatural way, around 6 hours into the 27th of October 2016, so this is about a week before the US election, it suddenly gets picked up by a whole pile of other accounts right across the political spectrum. Social media marketing, the European right wing, wacky conspiracy accounts, libertarians, the US right wing, and suddenly the hashtag goes absolutely wild. Now, this may be as a result of viral activity, but from having looked at these chronotopes that's the name of this kind of thing, it's a plot of various things over time, of other viral hashtags, they don't usually just all start like that. They grow more organically. You would expect to see a gradual and then accelerating increase in activity, not suddenly everybody covering it at once. So what happens here is bots and trolls flood this hashtag with trash. And then all of a sudden, it explodes everywhere and trends, but it's not the original intent trending, it's whatever the bots are doing, because at this point they have the volume and they control the discussion. If you want to see that activity that we talked about from the previous page, the constant every 6 hour posting, compare the posting signature from among, say, the social media marketing folks, where there are little spikes in activity, the purple down the bottom, or the other accounts, where it's just sort of like a blobby white line. Compare that with the regular drumbeat of the light blue posts at the top, US right-wing accounts, or the light green and the orange ones of the Russian posts near the bottom there. There's every 6 hours, all at exactly the same time, you can see that little ticker tape of dots, where suddenly all of these accounts are all posting at once. Now, I'm not going to claim that they're all bots, because when people see new tweets, they tend to retweet. And in fact, that's a pattern of activity we often see. Bots will retweet bots, but then humans will start retweeting them as well. And over time, a hashtag turns into absolute rubbish. But I think it's pretty clear to see from this, and this is some of the excellent work the Knight Foundation have been doing, that some groups more than others have their online discourse strongly affected by the presence of bots. And that's not to say I'm a conspiracy theorist, that's the data talking. And hey, if you look at the actual conspiracy theorist accounts, there's bot noise in there too. But you can see time in a lot of different ways. And when you start to think about plots of things changing over time, it's important to think that it's not always as simple as one straight line, the one number that something was over time. Things often occupy a range of data, and then those ranges change over time. Let me give you an example from my own work. This is some work I did in about 5 or 6 years ago, tracking what was normal and what was surprising in various different products. And so this one is a plot of CPU speed of phones over time, going right back into mobile phone history. So you can see that there's a very slow growth from the early 90s through to the mid 2000s, where CPU speeds are increasing, but honestly, not all that much. And then there appears to be an inflection point somewhere around 2008 or so when the rate of growth accelerates rapidly. There's two ways to think about that. One, this might just be an exponential phenomenon because as you can fit more and more transistors onto a chip, the final clock speed increases faster than linearly. It explodes up as the square or whatever, which is why you might see this as an exponential curve. The other way to think about it is that around about 2008 or so, we started using our phones as general purpose computing devices. This is when the first real popular smartphones took off with touch screens and with color and the ability to watch videos, etc. The iPhone and others in sort of 2006 through 2009 became a much bigger deal, and suddenly there was a need for phones to have much faster processors. It's probably not as easy to say that the technology follows the use case or that the use case follows the technology. In practice, these things tend to be a bit of both. But what I was interested in looking at here was, what's the range of normal? And can we then point to any products as being ahead of their time or behind their times? So you can see there's a couple of dots there that are definitely outliers. Let me explain this chart in the basics. The red line shows the median, the middle of the data over time. And then the lines around that, progressing through brown to green, show different standard deviations away. So you can think of the area between the two brown lines as the normal area where most of the data is, and then between the lighter brown lines is where even more of the data is. You can think of that as the range of normalcy. And then as that range expands, the width of what's normal gets bigger. As that range contracts, the width of what's normal gets smaller. We are tracking now not just a single data point over time, instead how a whole market, a whole product category is evolving over time. So you might say, 500 megahertz is slow for a phone, but it's important to note that in 2012, 500 megahertz was very slow for a phone. In 2009, it was normal, but it was first seen all the way back in sort of 2004, 2005. Here's another way of visualizing time, in this case as an animation. This plot, I'll show it to you, does not have time on one of the axes. Instead, time is shown as an animation. The bottom axis is, let me just see if I can pause this. So along the bottom here is the total confirmed coronavirus cases for that country on a log scale. Remember, a log scale, each tick is 10 times as much. So 1 case, 10 cases, 100 cases, 1,000, 10,000. Unfortunately, as the animation goes on, we're going to see much higher numbers than that. While the y-axis is showing the number of confirmed cases per day. So total cases over daily cases. And what this gives you is, as a fraction of the total cases, how many were there today? In other words, what is the rate of case growth over time? And we're going to look at a bunch of different countries that were unfortunately quite badly affected by the coronavirus pandemic as they explode upwards in cases, with time being presented as an animation. And what we're going to see is a really interesting trajectory. At the time where we've paused here on March 17th, you see that cases in China have already crashed downwards. This arrow moved down over the last couple of seconds of the video. Let me scroll back here and show that at first, when this chart starts, China already had a couple of hundred cases, or actually more than 1,000 cases, and was looking at getting hundreds every day, and it grew up along this trajectory, which we're going to get very familiar with, and then it starts to drop off. Social distancing, various restrictions have been able to reduce the number of daily cases. Obviously, you can't reduce the number of total cases. That's happened. That's history. So it doesn't move back to the left. It just moves down as the daily cases drop. So that trajectory is strangely consistent for almost every country that hasn't yet started doing things to control the virus. It follows as if almost on a line. Everybody is truly in this together because everybody is facing the same mathematics. That slope of that line is just a factor of how communicable this disease is. Everybody was looking at the same growth, even if they were looking at different cases at different points in time. And it's only once people start doing something to control the virus that they drop off that line. They drop down below that line and start to get control of things. They may have a lot of total cases, but they start to control the new daily cases. You see, China gets it down below 100 new cases a day quite quickly, and then with small outbreaks that are rapidly controlled, moves up and down slightly over time. South Korea initially gets things under control, and then at this point is facing a bit of a second wave. The various European countries go through waves of working and not working, and unfortunately the United States, Brazil, and to a lesser extent Russia just keep marching sideways. By October 2020, they're looking at well over 1 million cases, almost on their way to 10 million, and it just keeps getting worse. As we watch this, you'll be able to see that towards the end of last year, things start to improve in many places. Towards the end of 2020, sorry. You can see that when the line creeps up towards that angle, that trajectory, that means that things are starting to get away from a country. And then when it starts to trend back downwards, it means they're starting to get things under control. You can see this bouncing around, that these badly affected countries, the United States, Brazil, the UK, Germany, Italy, France, Mexico, Iran, you can see they're just ticking around. They're still seeing growth. It's just not exponential like it used to be. By January, however, things start to improve. Any guesses as to what improved in the United States on January the 20th, 2021? And after that point, you can see the US, for example, starts dropping down, as do many of the European countries. Brazil and Russia, and to a lesser extent Iran and Mexico, are still on struggle street with this one. I hope that will change too soon, as in more resources become available internationally. Now, I know it looks like only a small drop at the United States at the top there. They're still higher than almost any other country in terms of daily cases. But remember that it's a log scale, so reducing just a little bit actually means a lot. Dropping down to the next category reduces your cases by a factor of 10. Just for an idea, this is what Australia looks like on this visualization. Oopsie doopsie. So this is what Australia looks like on this visualization. Yep, here we are. Just to give you an idea, this is what Australia looks like on this visualization. You can see clearly the first two waves. Australia has some very early cases. By February, things are getting out of control. We go up along the main sequence, the trajectory with everybody else. By April, we drop off because we got things under control with a fast lockdown. We drop down to 10 or so cases a day, which at this point were mostly coming from international quarantine. That is quarantine of international arrivals. We bounce around in that space for quite a while. This was the window between our two waves. Then, unfortunately, by late June, things start to get out of control again in the Melbourne outbreak, and we dive upwards for the devastating second wave, which then starts to get itself under control about a month later. By the end of July, it slowly starts trending downwards in August, and then starts coming down much more quickly. What you can't see in this plot is how long it took for things to change, because this plot does not represent time in the x-axis, it represents time as an animation. So you can't see on this how long Australia spent at the bottom of its first wave. You have to watch the video to see that information. However, the advantage of this chart, this approach, which is invented by a data scientist called Atish Bhatia, which I've almost certainly said wrong, who really wanted to show how the trajectory was the same for every country. And this is a different way of representing time in order to do that. Here's another way of representing time. I get pretty good YouTube analytics on these videos, and I gotta say, folks, A lot of people are dropping off in the first 30 seconds. Check this out. Look at that pink highlighted area right at the beginning there. There's almost a third of you who closed this video in the first 30 seconds. What did I do? What'd I do? Is this something I said? I thought this was a pretty good video. What are you doing to me? I totally understand those of you who started closing the video 30 seconds towards the end there. You can see where we dropped down from about 50% viewership right down to a third. Like, sure, maybe you don't want to see my cheesy outros. That I'll buy you. But who are these people who are skipping to a minute into the video? You see that little spike there? Who are these people who are closing me down after the first 30 seconds? I can only assume that you're people who've accidentally clicked on the video a second time. I'll give you a pass on that. But I'm watching these analytics, folks. So what you can see here then is it's not representing real world time on the bottom axis. Instead, the time in the video. This was a 21-minute, 40-second video, and you can see what is the point at which people make these changes along the bottom there. Another way of doing of representing temporal data. But among all of these visualizations, in particular, the one of the mobile product data, where you could see that there was a wide range of what was going on, but also in the coronavirus data, and to a lesser extent in the YouTube data, we have to tackle, whenever we're dealing with time, with uncertainty. For a lot of data streams, we actually don't know what the exact answer is, because it's a range, or because we can't measure it exactly, or because there's a delay, or because we're guessing. We're very good at guessing, but we still need to be conscious of the fact that we're not guessing perfectly, whether we're guessing about our marks, guessing about a virus, guessing about a storm, guessing about our economy. Predictions are a huge part of data science and of data visualization. They're also something that I study a lot when I'm doing work in machine learning. And I want, as we go through this course, to bring you a little bit into what is AI and what are predictions and what are projections. And we're going to start talking about that now in the context of temporal data, because AI isn't that scary. We're not talking about Terminator, and we're certainly not talking about a whiteboard full of maths. I'm not actually sure which one of those would be more scary, but I'll leave it up to you. Minigun or matrices. What we're talking about is gaining an understanding of how these algorithms work so that you'll be able to design with them in the future. So the most simple part of thinking about uncertainty is thinking about ranges. You might remember how to deal with ranges of data back from high school. You will have studied histograms. This is a plot of the number of students on the y-axis who got a particular grade on the x-axis. And you can see here that the average mark was about 6, but marks clearly span the full range from 0 out of 10 to 10 out of 10. Only one student got each of those. But what this is showing is a distribution. A distribution is a probability word that means the range of likely values. So if I were to say, I've picked a student at random, what do you think they got? Well, the most likely answer would be 6, right? But you could also say, well, they probably got somewhere between 4 and 7. Because if you think about it, the vast majority of students exist somewhere between that 4 and 7 mark. So depending on how accurate you're willing for your guess to be, you could say, 6, or 4 to 7, or 3 to 8. And each time you give a larger range, you're including a larger fraction of your student base. I know this sounds kind of arbitrarily complicated, but the truth is that the real world involves a lot of uncertainty, and we're used to dealing in a lot of different places. Our predictions, the way we think about the future, a prediction of how long Google thinks it's going to take you to get to a place, a prediction of whether it's going to rain next week, your YouTube algorithm throwing up a video because it predicts you're going to want to watch that next. All of these things are based on predictions. All predictions contain uncertainty, and I think it's useful for you to get your head around some of these. Here's a way of visualizing uncertainty that some of you may be familiar with. This is a fan chart. Specifically, this chart shows time across the bottom axis, and then on the top axis, the y-axis, the estimate of unemployment in Australia. This is from the RBA's data from a February 2020 outlook, right before the pandemic. So you can see that they draw the line of their best guess up until the start of the blue region. That's the real data that they've observed, they've measured, but then the blue region indicates the uncertainty on their predictions, right? So the dark blue region, they say, okay, unemployment will 70% likely be within this range. So unemployment in early 2021 will be somewhere between 5.5% and 4.5%, roughly. 70% likely to be in that range. 90% likely to be between 6.25% and 3.5%. They have a whole bunch of complicated maths that goes into making that prediction. I mean, I don't know. I'm assuming that's how they get it. They could just roll dice. The RBA is pretty solid when it comes to these things, however. And this is called a fan chart, by the way. It shows the data up till now and then fanning out over the predictions that you're making. They're often used in these economic contexts. But predictions are not always right. What did the RBA leave out of their model? Well, they left out an incredibly unlikely but devastating to the unemployment rate event. Because let's look at what actually happened. This is from the RBA's outlook 1 year later. I think that link down the bottom is wrong. It should say 2021 February economic outlook. Because what happened in 2020 was that the employment rate wasn't between like 3.5% and 6%. It actually jumped straight up to 7%. And then their predictions now show that it would jump up to 10%. And the median predicted, the baseline, the model prediction is that it's going to be about, 9.75%, and then it'll slowly drop down over 2021, 2022. This is a different way of visualizing uncertainty, where they show just an upside and a downside, which are kind of best likely and worst likely outcomes. Upside and downside are finance terms. The upside risk means the risk of something getting more expensive, and the downside risk means the risk of something getting less expensive. Here, they're economists, so of course they're using finance terms. This shows that there's almost no chance. Look at how close together the upside and downside are on the model. There's almost no chance of unemployment being less than, say, 9% in the middle of 2021. Well, I don't have a chart for this one. RBA is a bit slow, but it is. Unemployment's back down below 8%. Whatever you think of the current federal government, and I could say a lot, they've done a pretty good job with stimulus, plus maybe it was not quite as bad as we thought. This prediction was wrong too. So they got the prediction wrong because they left out the possibility of a pandemic, and then they got the prediction of how bad it would be wrong again. All that said, the RBA are a pretty solid institution who do a fairly good job of predicting this stuff. I put these errors up to show you that prediction is hard. You always leave something out. You can never quite predict everything in the future because the future is full of unknown unknowns, to quote Donald Rumsfeld. You can build a model to deal with known unknowns, things that you're not sure of, but that you can kind of get a handle around, but you're never going to be able to capture something like a pandemic sweeping across the world. You can think about how likely it is, but you're never going to know when the next one's going to start. So that, I think, comes to one of the most important things that we need to keep in mind when we're thinking about using predictive models. Model, by the way, is just a statistical word that means a model takes in some input and gives out some output. In this case, when we're talking about temporal predictions, it takes in what's happened in the past, does some stuff, usually involving maths, and spits out a prediction of what happens next. That thing is a model of the future. It's not the future. It's a toy version of the future that only takes in some data. It is not actually a crystal ball, but it's going to give you some kind of prediction. But famous English statistician George Box says all models are wrong. They're only abstractions of the world, but some of those wrong models are useful anyway. We can make decisions even aware of the uncertainty of the future. And just because a model is sometimes wrong, because it sometimes doesn't predict our global pandemic, doesn't mean that we should throw out the model. It's usually a pretty good way to make decisions. Like, hey, there's gray clouds in the sky, I'll take an umbrella. As far as a model goes, that's a pretty crappy predictive model. You have a lot less data than a formal meteorological supercomputer, but you're going to be pretty okay, right? I mean, the downside risk is you end up carrying around an umbrella and looking like an idiot when it clears up at morning tea. And the upside risk is you're the only person who brought an umbrella even though the weather department said it wasn't going to rain. The model was useful. It's definitely not an accurate model, but given the consequences are so low, who really cares? So given this idea of uncertainty and trying to capture the likelihood of something happening, changing over time, we can go back and have a look at that mobile phone data. In this case, we can see the blue lines showing the contours of what's predicted to happen by our machine learning model. Red shows, by the way, back in history, where the model got it wrong. The model was way off in the 1990s because I guess the model just wasn't perfect, right? In the 1990s, things stayed absolutely static and the model didn't adjust to that all that well. For the record, this model is not using all of history to predict. It is predicting each moment using the data up to that point, as if it didn't know what would happen next, and then incorporating that data into its predictions for the next point. So it's predicting as a series, because I didn't want it to be able to use mobile phones from 2010 to be able to predict what happened in 2009, right? That's cheating. So that's why I got a bunch of things wrong in the early 90s, but I don't think anyone was really paying attention to mobile phone clock speed in the early 90s, so I'm okay with that. And that's also why you see that big band of white over on the left there. It just didn't have enough accuracy to make confident predictions about what was likely. It was just way off. The dark area after that, as the model starts to find its legs, the dark area is where it doesn't think a new phone would be. So it thinks it's very unlikely, come about 2007, that a phone would have 1,000 megahertz clock speed, because that was almost unheard of. In fact, I think it was literally unheard of at that time, looking at this data. So that's why it's a very dark, almost black region. But there's more uncertainty back around 2005, so there's lighter bands out there. It just doesn't really know for sure. You can use this to say, well, let's look at a specific phone. How surprising was it? Because that was what I was trying to get to in my analysis, right? So are these unusual products? Why are they unusual? What were they trying to do? What was creative about them? Take, for an example, this is the LG KC1. Smartphones tend to have fairly dull names. But LG released this phone. You can see that tiny white dot there. It was faster than anything around it. It was really ahead of its time as far as the silicon involved went, but it wasn't in 2007 or so all that much you could do with all that processing power. So the phone didn't really take off. It was ahead of its time. They'd put a lot of money into getting very, very high-end specs into the machine, but the product design just wasn't there. There wasn't something for you to do with a smartphone that fast at that time. This was pre-app stores. You couldn't play Flappy Donkey or whatever it is. You couldn't do anything. So the product was kind of a flop. For its very high price point, it didn't actually offer much in the way of features. This is the kind of analysis that I was doing back in my postdoc study in the US with some of my collaborators here. I didn't do this all by myself. This is myself, Douglas Fisher, Mary Lou Meyer, and Kate Brady, all researchers in this area, looking at back over time what products were surprising and why, not just on clock speed, but a whole bunch of different variables. And can we get a computer to say, hey, this one's really original, this one's really novel, it does things in an unusual or unexpected way. So I want to finish up by saying again that when you're representing temporal data, that is data that changes over time, you have a lot of different options, from the basic line chart all through to animations, spiral charts, chronotopes, all of these sorts of things. But that the most important thing to think about is, especially when you're thinking about the future, is that you need to be able to represent uncertainty. As data changes over time, you're maybe not able to measure it properly, or measure it perfectly at least. And then as we move towards the future, we have some idea, some model about what's going to happen. We have some idea of what the weather's going to be like in 3 days, but not perfectly. And for a lot of contexts, you need to be able to communicate how much you are guessing, how wrong you think you are, to your user. Later in the semester, we're going to cover a little bit about how to actually produce these predictions and how to know their accuracy, or their certainty at least. But for now, I just wanted to get you thinking about visualizing certainty, because it's something that's going to be a big part of assignment 2. Until then, I'll see you in class.